Hello, so continuing on problems from this week's weekly contest, let's see problem 3, maximum palindromes after operations. So basically with this problem, what we have is we have an array of words of length n, and you are allowed to do this operation any number of times, including not do it at all. And this operation basically is to choose two words. It can be even the same word, but choose two different positions, either from the same word or from two different words, and swap the characters. So what does that mean? So for example, let's say we pick two words, I and J. I and J can be equal, so it can be the same word, but then pick two different positions, X and Y, in those word I and word J, and swap them, right? So this is what this means. And the goal of the whole problem, you can do whatever number of operations you need to. You don't even need to count them. What you need to do is just return the maximum number of palindromes you can do after doing whatever number of operations you need to do. And palindrome is a word where basically if you read it from the front or backwards, it's the same word. So let's see, for example, here, this example. So how do we turn it into a palindrome? Well, we can swap the character in the first word, the first character in the first word, with the first character in the second word. So we'd have B here and we have A here. So now we have two palindromes here, and we have a third palindrome that already existed. So we have now three palindromes. And then just to illustrate the idea that you can swap the same word, let's take this one here. So for example, this one here, what we can do is swap the second character of the first word, okay, and swap the first character of the second word. So swap this one, okay. So now we'll end up with AAC and BBB. So this one is already a palindrome. Now, the second operation, we can take the second character, A here, and swap it with the last one. So that's what we do here. So you can see we can actually pick, I and J can be the same word. We can swap characters in the same word. And that way we get ACA, which is a palindrome, and BB is already a palindrome, right? Because this one, if you read it, the same word and its reverse is the same. And that's exactly what a palindrome is. So now we have two, so we return two. So that's the idea. Also, if you look at the constraint, they are very small. And so that means basically you could try to do some quadratic solution over n squared. And all of the characters are lowercase, okay? So let's just think about a couple of observations. So the first one is we are not counting operations. That's literally what the problem says here. We don't need to return the number of operations. You can apply any number of times, including zeros. We only want to know how many maximum number of palindromes we can get. You can do as many as you need. So that's important here. So we don't need to actually worry about doing the operation themselves. If we can come up with a shortcut, then that would work. We only care about the maximum number of palindromes we can get, okay? And so that basically tells you is you can redistribute all the letters freely among the words. Right? So you can maybe put all the words into one bucket and then distribute them in such a way that they are all the maximum is a palindrome, and that would work because you can swap any letters from any two words, even you can swap within the same word, okay? And you can do as many operations, there is no restriction. So you can just, you can actually just group the letters together and redistribute. The only constraints you have are that the words need to be a palindrome, as many as you can need to be a palindrome, but also the length need to be maintained because otherwise it's no longer the same one. No matter how you redistribute, you can accomplish that redistribution with the swap. And since we don't have a restriction on how many swaps we can do, you can just redistribute freely, right? So this is the key idea of this problem. And this is a good thing to think about with problems. It's actually, sometimes you don't need to do the actual steps that the problem says you need to do. If there is another way simpler to accomplish it, then that works, okay? Okay, so let's see here just hold that idea for a second, but let's think about just the definition of a palindrome. What is the definition of a palindrome? Well, the palindrome is the front reads the same way as the back. Like, for example, A, B, A. You can read it like this, you get ABA, and then if you read it right this, you get ABA. Another way to think about it is that if you reverse it, you will get the same word, right? Okay? Okay, so with this idea, oops, sorry. So with this idea, let's think about what is, sorry for a second here. So with this idea, let's think about what are the sort of the structures of a palindrome. So palindrome, you can have length even or odd, okay? If length is odd, then it's easier to see, because if length is odd, then you just need the front to be equal to the back, so that if you read in the front, it's equal to the back if you read from the back, but also so that it's equal to its reverse, right? Literally, that's what you need for a backend. So what does this mean, basically? This means that you need to have, for each character, if the length is even, you need to have the same character for the right. So you need to have each character twice, okay? A left instance and a right instance. Basically, sorry about that, you need to have symmetry, right? Now, if the length is odd, still the same applies, but you need to have something in the middle. That can be any character, right? It can be even one of the other characters that exist. It doesn't matter. But what matters is that except one, everything else needs to be twice. Every other character needs to be twice. Okay. Okay. So that's that idea. Now, if we go back to the idea we mentioned here, where we said we can distribute all the letters freely, so that means basically we can take the words and put them in one bucket. Just take all the characters of all the words, put them in one bucket. But since here in the palindrome, we need to know how many times a character occurs to see if we can make a palindrome. Because let's say if we have character C, if we have it only once, we can't use it for the sides of the palindrome. So we need to know how many times that character occurs. So we can just take the words and actually put them in so we can take the words and actually put them in sort of a counter. So let's say if we take from this one, for example, this here, okay? What we need to actually do is create a counter. So A occurred 1, 2, 3, 4 times. B also 4 times. Okay? So once we do that, we only need to care about how many palindromes we can get, right? Because as I said earlier, you can just do the swaps to do the same thing as placing the characters freely in whatever position you need to. Okay, so we said we will count, like do something like what we did here with this. Now, once we do that, again, going back to this, we need the characters to be in pairs so that we can construct a palindrome. We will for now, let's just ignore this middle one. We'll come back to it. But for all the other cases, we need pairs of letters, okay? And so going off that idea, we need pairs. And so, let's call this count just so that my notation here matches. Okay, let's actually keep it occurrence. And so we need pairs, so we need to know how many pairs we can get. So to get that, we can just, for each letter's occurrence, which this occurrence values will give us, we need to divide it by 2 to know how many pairs we can get. So in this specific case, that means we will get, so for A, we can get 2 pairs of A's. For B, we can get 2 pairs. And so if we add this up, we can have 4 pairs, right? And literally, if you think about this is exactly what happens. We can have, for example, A, and then A here for the first length, and then we can choose either to add the same pair again, or we can choose to add BB, that is the same. And then for the second one, we can choose also to have AA or BB. For the second one, if we choose AA, then the second one has to be BB, right? So you can see how many pairs we utilized. We utilized one here, and then a second one here, and then a third one here, and then a fourth one here. So we utilized 4 pairs to make these palindromes. Okay, so now let's go back to here. So to maximize the number of palindromes, so the goal of the problem, if we go back to it, is to maximize the number of palindromes. And obviously, regardless of the number of pairs we have, we would have more chance of getting a palindrome of a string of length 2 than a string of length 4. Okay, because this one will need only 1 pair, this one will need 2 pairs. Okay, and so it's easier for us to make a smaller length. This is just intuitive, right? And so what does that mean? That means let's just sort the words by length so that we can maximize the number of palindromes we can get. Okay, and so we do that. And so we do that to maximize the number of palindromes we can get. And that's the core idea, pretty much. That's pretty much it. So once we sort by length, let's take this example again. What happens? So these words, if we sort them by length, let me actually just remove this. We know we have 4 pairs. So if we sort by length, then we have length 2, 2, and length 4. So these are the lengths. So first we try to accomplish length 2. We can accomplish it. We take 2 of the pairs we have, and so we accomplish it. So we have 1. And then, so this one is done. Because the length is 2, we only need 1 pair. This one, the length is 2. So we need also another pair. Do we have more? Yes, because now we have only 3 pairs. So we do this one. And now 4, we need to be able to accomplish 4 here, we need 2 pairs, right? Length 4 means we need 2 pairs. After this one, we have 2 pairs left. So we have 2 pairs left, so we can accomplish this. And so now we have a third one, okay? So if we try to code this up, what does this mean? So that means basically to be able to get a palindrome for a length, then we need basically pairs, the length divided by 2. That's basically the number of pairs we need, okay? The number of pairs needed is L divided by 2, right? And so we can just check if we have still more pairs, we can just divide it by 2. Now, let's just assume, for example, we had CD here, for example. So we have 1C, 1D. And so the number of pairs we have is still just 4, okay, because we don't have C. C is just once and D is just once. And so we have one more length, which is here, 2, okay? And then now we have 4, okay? So we accomplished this one, and now we have only 1 pair left, okay? So we have 3. Now what about, now we need to accomplish the one with length 4. So this one needs pairs, 2 pairs. But we only have 1 pair, so we can't do this one. And so we stop. So when do we stop? When basically the number of pairs we need is more than what we have left of the pairs that we determined from the count of characters that the number of pairs we have. And that's the core idea of the solution, okay? Now, going back to what I mentioned here about this middle element, if one of the lengths is odd. The idea here is it doesn't matter because since the character length, since we put all the characters in a bucket, the number of characters is still the same. So if something we weren't able to accomplish it with the pairs, we still have a number of characters that are not pairs that are remaining. We can use whichever one we want. It doesn't matter because this position in a palindrome can be anything. Okay, and so that means basically we don't even need to worry about it because we can pick whatever remaining character. For example, in this specific case, let's say maybe this was, for some reason, maybe this was let's pick another E, for example. Okay, so in that case, and maybe this was A, just to make this simpler. Now A is 5, so we are able to construct this. uh, sorry, let's actually keep this CD 4. So we are able to construct this. Why? Because we can take either C, D, or E. It doesn't matter, and put it in the middle. Okay, and so that's the core idea here. So now what's remaining is just to code this solution up. But the idea is put all the characters in a bucket, get how many pairs you can accomplish, because for a palindrome what matters is pairs of the same characters. See, start from the smallest length first, try to get as many palindrome from the smallest first to largest length. Try to get as many as you can, and when you can't anymore with the pairs you have, stop, and that would be basically the maximum number of palindromes you can get. So it's sort of a greedy solution here. So let's code this solution up. Sorry. So first we said that we need a counter here for how many characters we have. So that's what we'll create. So this would be a counter, and then we need for each word to just go through the characters. For C and W, we will increment by 1. So we'll put them all in one bucket in this counter. And then what we need to do, we said, is we need to know how many pairs we have. And the pairs are just, if you look at what we did here, for A we have 2 pairs, for B we have 2 pairs. So it's each count divided by 2. So we take each count, we divide it by 2. For the count is in the values of the occurrences. So for each character we take the number, the count, and divide it by 2. But overall, how many pairs we have, it's the sum of these. That's what we did here. And so that's what we will do like this. Okay? Now from this here, what should we do? Well, we need to get the lengths, and we need to to go through them in order from smallest to largest. And so to get the lengths, we can just say this is the length of W, and we go for each word. And now we can go for each length, but we need it in sorted order. So we go through each length in sorted order. And now we just see what we did here. Every time we used a pair, we subtracted it. So we used a pair from this 4, we subtracted it by how many we used. And for example, here we used just 1 to get length 2, and we subtracted by 1. And so that's exactly what we are going to do here. How many pairs we need? So let's call them pairs needed for L. It's L divided by 2, right? If you have 4 characters, you need 2 pairs. If you have 7 characters, you need 6 divided by 2. You need 3 pairs, right? And then the middle one, as we said, can be anything. And so this is minus the pairs we need for this length. Now we need to make sure this is possible. So maybe pairs we have, just to make this super clear. So if the pairs we have is bigger than this, then we can accomplish it. Okay, and then, but if it's not, that means we can't. So we stop here because we reached the maximum number of palindromes we can get. So at this point, we can return the number of palindromes. Now we just need to initialize this. Now, if we have the number of pairs we need, we can accomplish them with what we have. We need to increment the number of palindromes because we will be able to make this palindrome, right, for this length. And now what we can do at the end, we can just return. Let's say maybe we were able to accomplish it for all of them. Then in that case, we can just return the number of palindrome. So actually, I made a small error here. So we need equal, right? Because if what we have is exactly equal to what's remaining, basically is exactly equal to what's needed, then we can still do it, right? And so in that case, let's run this. Looks good. Let's submit. And that gets accepted, okay? And that's pretty much it, actually. If you take a look at the solution in terms of time complexity, this is of number of words by the number of characters per word. And since we know the length here are not too big, so this should pass. And then this side here is of n log n being the number of, n being the length of the number of words, basically. And so, yeah, n log n with n multiplied by, let's call it k, which is the maximum number of characters for the words, right? And space, we are using this extra space with this one, which would be of, again, the number of characters overall. So at most, that's going to be 26 because we have only lowercase English letters. So it's constant here. The length here are O of n. So O of 1 for the counter because it's just 26. The lengths are O of n though. So O of n space and O of n log n and n multiplied by k, which is the maximum length for a word. Okay. Yeah, and that's pretty much it for this problem. Thanks for watching. I hope this was helpful. Thanks for watching and see you on the next one. Bye.